Hey everybody, in this video I'm going to work through a bunch of example problems and solutions for Exam 3 Probability and Statistics Calculus based. Most of the video will involve a lot of statistics, confidence intervals, hypothesis testing, thinking about the type 1 and type 2 errors, power of a test, that kind of thing. But we will, especially near the beginning, have also some problems related to more theoretical probability, including a curve of regression problem and also estimators, unbiased estimators, method of moments, method of maximum likelihood, that kind of thing. So we're starting off with a fairly simple problem related to statistics. Consider the random variable t12. What is that? That is a t-distribution with 12 degrees of freedom. The subscript here means the degrees of freedom, df. The goal of part A is to find a number labeled little t sub 0.05. Is that related to this? Yes. Well, it's assumed the degrees of freedom is still 12 here. This subscript does not refer to a degrees of freedom. It represents, well, I like to describe it as an area to the right. What does that mean? It means that if I draw a t-distribution, in this case with 12 degrees of freedom, which looks like a normal curve for all you can tell, unless we are real careful about the scale, and draw this number on the axis. I want to draw it so that the area under the curve to the right of that number is 0.05. That area should be 0.05. That is what this notation means, little t sub 0.05. It's assumed that we are still considering a t-distribution with 12 degrees of freedom. I'll show you how to find this in two ways. One is with a table. So we'll open my textbook up that I use to the table for a t-distribution. Here it is. In this table, the degrees of freedom, gamma, is along the column over here. We're looking for 12 degrees of freedom. That's this one right here. These numbers right up the top here, you can see, are labeled as really CDF values, cumulative distribution values. They're probabilities that the random variable t sub gamma is less than the given number little t, where the given number little t is in the main body of the table. You can see in this picture, t is on the axis, this little t. So we're looking for t sub 0.05, where the area to the right is 0.05. Therefore, the area to the left is 0.95, 1 minus 0.05. So I need to look for 0.95 in the table for 12 degrees of freedom, and I see 1.782. That is the answer for part A of this first problem. T sub 0.05 is 1.782. Let me also show you how to find this with technology. With a TI graphing calculator, we can go to the distribution menu, which is right above the variables button there. Distribution menu, and look for inv-t, meaning inverse t distribution, which is going to give you a value on the axis rather than a probability. We're going to need to plug in a probability into inv-t. The area refers to the probability. It's assumed to be a CDF value, so this is an area to the left. So if I want the area to the right to be 0.05, once again I want the area to the left to be 0.95. The degrees of freedom is 12. And I confirm the answer to be 1.782. Okay, so that's a way to confirm the answer. Part B is a pretty similar kind of problem. We are still finding a point, t, a number, on the axis, where the probability that this capital T random variable with 12 degrees of freedom is less than or equal to little t is 0.99. In other words, I'm trying to find t sub 0.01. Okay, let's just do it with the technology. So I go back to inv-t, and now I want the area to the left to be 0.99. And what do I get? I get a bigger number. I get 2.681. 2.681. Okay, it's still the same distribution. It's still the same picture. It's still a t-distribution with 12 degrees of freedom. But now I'm after t sub 0.01. That's got to be further to the right of t sub 0.05, because the area to the right of that has to be smaller than 0.05. It has to be 0.01. Okay, that's what we get. You can check that with the table as well. On to problem 2. The Hobbit, An Unexpected Journey extended gift set was released back in 2013. The prices recorded for a number of online retailers were these: 1, 2, 3, 4, 5, 6, 7 numbers. So this is a random sample of size 7. N is 7. Assuming the prices listed are for a random sample, like I just said, from a normal population of all online retailers. Okay, so there's some big population out there, and we'd like to know the true population mean, mu. That's the background here. That's what we're after. We want to calculate a 95% confidence interval for the mean price. And we're going to make, it's really an unrealistic assumption. We're going to assume that we know what the population standard deviation is. Now, if you think about that, that is very unrealistic. Why would you know the population standard deviation if you don't know the population mean? The reason we do this is because when we first think about confidence intervals, it's easier to think about it in the context of pretending we know what sigma is. Later on, in fact, later on in this video, I'm going to do a situation, a very similar kind of problem where I want to find a confidence interval when I don't know sigma, and then I need the sample standard deviation, typically labeled with an S. But here I'm pretending that I know sigma, okay? Just for the sake of keeping it simpler. Show your work, okay? There's a formula. In terms of random variables, we could write the formula for the confidence interval as capital X bar, where this represents the statistic capital X bar from the random sample of random variables, capital X1 through capital Xn, plus or minus z sub alpha over 2, where that subscript, just like in the first problem, refers to an area to the right. Alpha is related to the confidence level. If it's 95% confidence, alpha is 0.05. If you don't know how to figure that out, what we typically do is we write the confidence level as 100 times 1 minus alpha percent. If this equals 95, that means 1 minus alpha is 0.95, and so alpha is 0.05 in this case, and alpha over 2 would be 0.025. Then we multiply this times the fraction, that is the population standard deviation, which we're pretending that we know, divided by the square root of n. This is really a random variable. It's really two random variables, a left endpoint and a right endpoint. I wrote capital X bar. However, we are going to observe a value of X bar. We would typically write that as little x bar by plugging these numbers into our calculator and computing that observed sample mean. I did that already. I plugged the numbers into the calculator. You'd want to go to the stat menu. Oops, not that one. Stat menu. You'd want to go to edit. And in list 1 over here, I plug these numbers in here already. 54.74, 56.93, 54.01, 56.94, 55.94, 62.95, and 68.95. Yes, they are in there. That is a sample of size 7. So what is the observed value of X bar? Go back to the stat menu. Now go to calculate one variable stats. It's list 1. Be careful about that kind of thing. If you've got more than one list, calculate. X bar, the observed value, is 58.637 approximately. 58.637. Of course, you could also round that to 58.64. $58.64. That's the observed value of this point estimator. It is a point estimate for mu, the population mean. Is it likely to equal mu? No, it's not likely to equal mu, but we hope it's close. And the confidence interval gives us some idea of how close it's likely to be when we pretend we know sigma and when we assume we're coming from a normal population and that kind of thing. Okay? Is it really a normal population? That's another point to debate, but we are going to assume that here. What is z sub alpha over 2? Again, alpha is 0.05 here, so alpha over 2 is 0.025. With a calculator, well, maybe this is something you remember. It's 1.96 is the answer. That's one of the numbers people remember coming out of stats classes. But if you wanted to confirm that with the calculator, you go again to the distribution menu, this button here, and we'd want to look for inv norm. Area to the left, careful, is 0.975. 0.975. And we are talking about a standard normal distribution here when we think about z. Mean of 0, standard deviation of 1. Paste this. And yes, you get about 1.96, okay? But this is a number many people remember even long after a stats course is over as a z value for a 95% confidence interval. Again, sigma is, we're pretending we know, is 5.25, and n is 7. So Putting this all together, our observed 95% confidence interval for this particular random sample is going to be 58.64. I'll go ahead and round it to the nearest cent, plus or minus 1.96 times 5.25 over square root of 7. 5.25 divided by square root of 7, that's about 1.9843, multiplied by 1.96, and round to the nearest cent, and the margin of error here is going to be about $3.89. Hopefully no mistakes here. I'll make notes on the video if I do make mistakes. So we can write the answer, including units, as $58.64 plus or minus $3.89. Emphasizing when the confidence interval is written in this form, what the point estimate is, the center of the interval, and also emphasizing the distance between the center, the midpoint of the interval, and the numbers on either side. This is 389. But we also could write this in interval notation, and it really doesn't matter whether you use square brackets or parentheses. It doesn't really matter if you include the endpoints or not. It's not a real big deal. We're just after approximations anyway. So the left endpoint would be 58.64 minus 3.89, and maybe I should have kept more decimal places because in rounding too early this could lead to a small error, but I won't worry about it. 54.75 is the left endpoint, and the right endpoint is 58.64 plus 3.89, $62.53. So what we say is we're 95% confident that this interval contains the true unknown population mean price for the entire population, all these retailers selling the Hobbit here. Okay, we're 95% confident in this. Does this mean the probability that mu is in there is 95%? Technically no, because we've already done the sampling, and so it's either in there or not. It doesn't really matter too much. I mean, as far as betting odds, you'd probably still think of your odds as being 95%. Your probability of it being in there is 95%. Technically speaking, when you say the 95% confidence interval, you're referring to your probability before the fact. You say, I'm about to random sample. What are the chances that when I do my random sample of size 7 from this population that it's going to capture mu? 95%. Or another way to think of it is if you do the sampling over and over, many random samples of size 7 and compute many different confidence intervals, different samples will give you different confidence intervals, about 95% of them will contain mu. Which ones do and which ones don't, that's hard to say because you don't know mu. All right, on to number 3. This is a more theoretical problem. It looks kind of hard, especially if you're not familiar with the method of moments, but it's actually a pretty easy problem once you know your concepts and once you understand the method of moments. What is this about? Got a bunch of capital letters. These are random variables. This is a random sample as a bunch of random variables, independent random variables with the same distribution. Distribution is binomial with parameters n and p. So anytime you observe a value of one of these random variables, you're observing the number of successes in n trials where your probability of success on each trial is p. I always talk about shooting free throws, pretending you're standing in a free throw line, no pressure, no game situation. You're just shooting free throws. Maybe you're going to attempt 10 free throws and your probability of success is 0.7, and x represents your number of successes. How many do you make in 10 attempts? Sometimes it could be 5, 6, 7, 8, 9, 10. I suppose 10 probably would be unlikely, but it could happen, especially if p is large. You would be observing values of these random variables in that case. Our goal in this problem is to use the method of moments to find an estimator p hat for p. Putting a hat above a parameter emphasizes it's an estimator, which is a statistic that you can compute from a random sample. And we'd hope it would be a good estimator for p, but we want to be official here in using the method of moments. Now, without using the method of moments, you should be able to reason out a logical estimator for p. Think about it logically. You know, maybe the first time you shoot those 10 free throws, you make 8. The next time you shoot those and you make 6. The next time you shoot and you make 7. The next time you make 9, etc. What would be a logical way to estimate your true probability of success on each free throw? One way to do it is you could take those numbers, 6, 7, 8, 9, etc., average them, find X bar, you get something like maybe 7.23 or something, and then divide by 10, the number of attempts for each one of those. 7.23 divided by 10 would be 0.723. That would be a logical estimate for P. And that's probably what we should expect with the method of moments. But how does it go? You need to first, step one is to first write down how, well, in this case, the first moment is related to the parameters, N and P. So that's step one, okay? Write down, when you're trying to find an estimator for P in this case, you want to have an equation that involves P in terms of first moments. Sometimes it can involve second moments as well. Like if you do a method of moments for the two parameters of a gamma distribution, it will involve thinking about both the mean and the variance, and you need both to think about the first moment and the second moment. But here, since the P is in a simple equation involving the first moment, we can just do it this way. Second step is to replace the expected value of X, the first moment, by a natural estimator for it. That's easy. That's X bar. That's a natural estimator for the first moment, mu, you could call it. It's also traditional with the method of moments to call this M1. If you were estimating a second moment, EX squared, you'd call it M2. But we're not doing that here. But M1 is X bar, a natural estimator for mu, the expected value of X, which is a parameter. And you replace the parameter you're trying to estimate, or you're trying to find an estimator for, with its estimator, the notation for it at least, P hat. And then the third step is to try to algebraically solve for the estimators. That's very easy here. All we need to do is divide by n. P hat is X bar over n. And that's the exact same thing I said was a logical thing to do. And careful here. Let's see. Yeah, that's the exact same thing I said was a logical thing to do. Take all your numbers, average them, and divide by n, okay, which for my free throw example would be 10. Got a little confused there by one thing. This random sample has size m, and you don't see an m anywhere, and that's not a real big deal, but you could get the m involved because you could write X bar in terms of m. You could say X bar is the sum I goes from 1 to m of xi divided by m. So you could also write P hat that way. Okay, that would be valid as well. All right, on to the second page. Lots of problems, lots of good practice problems for this video that I've got for you here. This next one involves moment generating functions and something I call the fingerprint theorem. I don't think everybody calls it that. It's thinking about the moment generating function as being like a fingerprint, an identifier for a random variable. We're supposing X is normal, and means normal, with mean 20. And in our textbook that I use with my students, this second number represents the variance, sigma squared, 25. Some textbooks write the standard deviation there. So this is supposed to be a sigma squared here. If your textbook writes standard deviation, you'd want to adjust. And y is meant to be have a normal distribution with mean 15 and variance 36. Note that the MGFs of these random variables, moment generating functions, are these formulas. Why? Because for a normal distribution with mean, mu, and variance sigma squared, the MGF, moment generating function, is that. And so for the x's case, I'm replacing mu with 20 and sigma squared with 25. And for y, I'm replacing mu with 15 and sigma squared with 36. Okay? But it's good to note the general fact there as well. Now, I gave these to my students for this problem. I didn't have to. And for my students, you should be able to look that up in the table, what the moment generating function for a normal random variable is. But this helps save time and helps save mistakes and that kind of thing. Part A says, assuming x and y are independent, common assumption to make, use a theorem and properties of exponents to find and simplify the moment generating function of x plus y. So the theorem is this. The moment generating function of the sum of two independent random variables is the product of their moment generating functions. That's the theorem. I just called it a theorem. It's not the fingerprint theorem. It's not saying what the random variable is based on the moment generating function. It's just a property of moment generating functions when you have the sum of two independent random variables. The moment generating function for that sum is the product of the corresponding moment generating functions. And we are assuming independence here, as we often do. As far as properties of exponents go, to find and simplify this, I need to use the formulas that are given, and I need to add the exponents, because that's a property of exponents. The moment generating function for x is e to the 20t plus 25t squared over 2. That's all an exponent of e. And the moment generating function for y is e to the 15t plus 36t squared over 2. I have not used the property of exponents yet, and now I'm going to add the exponents, and in this case, combine like terms. So you get e to the 20t plus 15t is 35t, and 25t squared over 2 plus 36t squared over 2, you already have a common denominator of 2. 25 plus 36 is going to be 61t squared over 2. That's a property of exponents. Okay. Part B says, use part A, the result here, and the fingerprint theorem, again, maybe not everybody calls it that, to describe the distribution of x plus y. Briefly describe how the fingerprint theorem is relevant, okay? How is the fingerprint theorem relevant? Again, it says that a random variable is completely determined by its moment generating function. If you know the moment generating function, then you know the random variable. You could write what I just said there. The fingerprint theorem implies or says that knowing the moment generating function tells you what the random variable is, identifies the distribution of the random variable. Might be the best way to say that. Distribution of the random variable. And I'm not going to write any more words, but let me say some verbally. Since moment generating function for a general normal random variable with mean, mu, and variance sigma squared is this, and since that has that kind of form with mu equal to 35 and sigma squared equal to 61, therefore, 3 dots means therefore, x plus y is normally distributed with mean of 35 and a variance of 61. Okay? You could say more. Okay? This probably would be good enough for full credit for my students in writing it that way. All right, on to number 5, which is a long problem, but often with my students, when I make long problems, they're actually fairly easy if you know what you're doing. It just takes a while to read. It looks scary because it's so long, okay? But just practice these kinds of things, and that's why I'm putting it in the video. I have more long problems like this. Let X denote the price paid in hundreds of dollars for a barrel of crude oil by initial carrier, and let Y denote the price paid in hundreds of dollars by a refinery. Okay, the meaning of X and Y is not such a big deal here. We're just trying to get on to the math. Assume the joint density for the bivariate random variable X comma Y is given by this formula over this domain. I guess we will think about the application briefly here to see if this makes some intuitive sense. Careful, this is a triangular domain. I only put rectangular domains for bivariate random variables on exam 2. Or at least that's been my practice so far. Exam 3, we could have a triangular domain, and that's the case here. Make a little picture. X and Y are both between 0 and 1. And the way you want to think about this set of inequalities, besides the fact that they're both between 0 and 1, is you first want to graph the equation y equals x, maybe as a dashed line, because That's a strict inequality. It's not a real big deal, though, that it's strict. And we're looking for all points in the unit square where x and y are both between 0 and 1, where y is also less than x. You got to be below that line for y to be less than x. All of these points have the property that their second coordinate is smaller than the first coordinate because they are below that line. Okay? It's real important to be careful in thinking about how to draw that. That takes practice. Well, okay, I even told them what it was. It's filled in rectangle or triangle with these vertices. Okay? There it is. The marginal density for x is therefore this. Now that's the general formula for the marginal density. And notice the upper limit of integration is not a constant, it's x. Remember that in general, you need to integrate the joint density with respect to y to integrate out the y to get the marginal density for x. When you think about this equation, you need to think of x as fixed. You need to imagine that you've got some fixed number x here on the x-axis. And for that fixed number x, you are taking the joint density and doing a single integral, not a double integral, with respect to y in the vertical direction. For that given fixed value of x, what does y vary between? It varies between the second coordinate of the first point here on the x-axis and the second coordinate of this point on the line y equals x. It varies from 0 to x. You want to get it in terms of x. The coordinates of that point are x, y, but y equals x on that line, so you can think of the coordinates as xx, and the coordinates of this point as x0. Y is varying between 0 and x. You want it to be an x so that the final answer here depends on x. Again, when you're doing the integral, you think of x as fixed. But then you do the integral and you get to x, and then you say, oh, I can think of x as a variable. And that would be the marginal density, and it is for all x between 0 and 1. And it is a density. If you integrate this thing from 0 to 1, you do get 1. X squared going from 0 to 1, you get 1. Okay, it is a valid PDF, probability density function. All right, to save time, and I'm telling them answers here, here's where they're going to do something, or you are going to do something. Next thing, this means that the conditional density for y given x, this is a random variable modeling y values, prices paid by the refinery. Y being less than x, by the way, means that the refinery pays less than the initial carrier. Okay, does that make sense? I guess so. Actually, I think it should be the other way around, perhaps. I'm not sure, and I don't want to take the time to think about it. Anyway, coming back to this, you're trying to model y values when you pretend you know that capital X equals some fixed number little x. And the formula for such a thing is this. And when you look at this formula, you need to think of x as fixed and y as the variable. And you get this, plugging 2 in there in the top and 2x in the bottom. It's 1 over x for y between 0 and x when x is fixed. And when x is fixed, this is a constant function. It's a uniform distribution. The graph of 1 over x as a function of y is horizontal. The value there is 1 over x. It goes between 0 and x. The area under that is 1. 1 over x times x is 1. Okay? It is a valid PDF. You want to think of x as fixed there. But I could do this for different x's. Here's your job. Show your work to do an appropriate integral to find and simplify the formula for the curve of regression of y and x, this function, that's giving the mean, mu, of this variable as a function ultimately of x. When you do the integral, you once again think of x as fixed. We're doing a mean of a y variable, a conditional y conditioned on capital X equaling little x. It's a mean with respect to y. It's an integral with respect to y. An integral for the mean, it means I need to multiply the variable times the PDF. with respect to y. And then in the end, the answer is going to depend on x. And so we could say it's a function of x. What are the limits of integration? They're the limits of integration based on this fact that the conditional density here is 1 over x for y between 0 and x. There, y goes from 0 to x. So this becomes the integral from 0 to x of y times 1 over x with respect to y. I'll write it as 1 over x times y, thinking of 1 over x as a constant. Integrate that with respect to y, you'll get 1 over 2x times y squared. Y goes from 0 to x. Plug in y equals x, you'll get x squared over 2x. Plug in y equals 0, you get 0. And this simplifies to x over 2. And that is the final answer for this mean. I do say, here's another hint, the final answer is fairly simple and should make good intuitive sense. For example, if you graphed it and thought about the relationship to the formula for the joint density and its domain, why does this make good sense? If I graph it over here, graph this function of x, it's going to be a line through the origin with the slope of 1/2. It's going to look like this. For a, for any given x, the mean value of y along that interval, since it's a uniform distribution, is halfway through the interval. It's the midpoint. That makes good intuitive sense. Because it's a uniform distribution overall, the joint density is 2, so its graph is horizontal plane, and effectively probability is evenly distributed. We also know this fact that it's uniform, that this conditional density is uniform. That makes good sense. Okay? All right. You might want to try to find the other curve regression for x on y. I don't think it's guaranteed to be linear in that case, but I'm not sure. I'm thinking of another example. Maybe it would be. But go ahead and work to find it. On to the next page, number 6. Is about, it's good to look for what a problem is about first. Method of maximum likelihood. You can see a likelihood function there. Sometimes we also maximize the log likelihood function. And again, for sake of helping my students and helping them avoid make mistakes, so it makes grading easier on me as well, I didn't do the most general kind of problem. I'm not doing an arbitrary random sample. I'm doing a particular random sample of 3 numbers and observed values there. In terms of x's, you'd label these as little x's instead of capital X's. These are observed values of a random variable. From a binomial distribution, the sample is of size 3, so m represents the sample size. The binomial distribution has parameters n equals 4 and an unspecified probability of success p. The PDF, or probably better to call it a PMF, probability mass function for this discrete random variable, is f of x, which is the probability that capital X equals little x, is 4 choose x times p to the x times 1 minus p to the 4 minus x. Binomial. You know about binomial random variables. You've seen this before. What's our goal? Our goal is to estimate p, the true probability of success. Once again, think about it intuitively. What should the answer be? These are your numbers, your observed values of x. 2 plus 1 plus 1 is 4. If you average those, it's going to be 4/3, 1.3 repeating. And that divided by 4, 4/3 divided by 4 is 1/3, should be the logical answer for the probability of success on any given trial. Like if my probability of making the free throw is 1/3, 0.3 repeating, this would be, doing 4 free throws. The first time I make 2, then I make 1 out of 4, then I make 1 out of 4. 4/3 is the average of those numbers. Divide by 4 is 1/3, is giving me my estimate for my probability of success. We're doing that by maximizing a likelihood function or a log likelihood function. The likelihood function in the discrete case is the product of the PDF values, or PMF values, which in this case is f of t 2 times f of 1 times f of 1. And this does, in the discrete case, represent the probability of observing x1 equaling 2 and x2 equaling 1 and x3 equaling 1. It's a product of probabilities by independence. In the continuous case, you still multiply PDF values, and those are PDF values for the continuous case, but it's really no longer a probability. That's what the method does. If you plug these numbers in, x equals 2, then x equals 1, then x equals 1 into this formula, in terms of p, it simplifies to this function. So saving time, saving work, hopefully saving mistakes. We want to maximize this function. Hey, that's a Calc 1 problem. Maximize this function. I'll do it both ways. I'll maximize this likelihood function. I'll also take the logarithm of it to maximize the log likelihood function, which is a little easier to do. What's the derivative of L of p? Don't expand this out. That would be a lot of work. Just use the product rule. The derivative of the first function, 96 times p to the fourth, would be what? 384p cubed. 96 times 4 is 384, yes. Times the second function, 1 minus p to the eighth. And then plus the first function times the derivative of the second. I'll bring the 8 down. I'll also get a negative 1 from the chain rule, so I'll get a minus 96 times 8. That would be what, 768? Yeah, okay. P to the fourth, 1 minus p to the seventh with the chain rule. That's where the minus sign comes from. So I use the product rule and the chain rule. I want to set this equal to 0 and solve for p, the critical point, which I'm hoping will be a maximum, and it will be. I'll argue graphically. That looks complicated, but it's easier than it looks. Factor out any common factors. There's a common factor of 384, a common factor of p cubed, and a common factor of 1 minus p to the seventh. And what's left over after factoring out is, in this first term, a 1 minus p, and in the second term, just a minus 2p. This is 0 certainly when p is 0, and when p is 1. It's also 0 when 1 minus 3p is 0, and that's going to be our maximum likelihood estimate. 1 minus 3p equaling 0 means 3p is 1, and there we have it. P is 1/3. And I'm writing this without a hat. I mean, you could write a hat and call it an estimate from the maximum likelihood method. Either way is okay. You could write a p hat. You don't have to think of it in terms of estimation. You could just think of it in terms of the directions of the problem. I'm finding the value of p that is most likely to have given us these values by maximizing this likelihood function, which represents the probability of observing these values. Is it really a maximum? You could try using the second derivative test or the first derivative test. If you graph it, you'll see a graph that looks about like this. Excuse me. And it's maximized at 1/3. Okay, that's L of p as a function of p. Excuse me, I have a bit of cold. All right, take a drink here. Here's the second way to do it, is to maximize the log likelihood function. I call that LL of p. It's the natural log of the likelihood function. So it's the natural log of this thing here, 96 p to the fourth times 1 minus p to the eighth. And using properties of logarithms, which is definitely what you want to do here, this can be written as ln of 96 plus 4 ln of p plus 8 ln of 1 minus p. And it's because of those properties of logarithms that the log likelihood function is often easier to optimize than the likelihood function itself. Where the log likelihood function is optimized, maximized, the value of p is the same value of p that maximizes the likelihood function, because the log is an increasing function. Okay, it's monotone. We want to differentiate this. We get 0 plus 4 over p, and then from the chain rule we get minus 8 over 1 minus p. Set that equal to 0. Solve for p. We'll get 4 over p equals 8 over 1 minus p. Cross multiply. Gives 4 minus 4p equals 8p. Add 4p to both sides. Get 4 equals 12p. And now divide both sides by 12. P is 4/12, which of course is 1/3. We get the exact same value of p that optimizes, maximizes both the likelihood function and the log likelihood function and solves the problem. Okay? So that is the answer, 1/3. And you can write it either as a p or a p hat. Next problem is statistical hypothesis testing. Gasoline pumped from a gas pump, that's a typo there, I guess, from a gas pump at a particular gas station is supposed to have a mean octane rating of 87.3. Okay. Government agency suspects the gas at this station has a lower octane reading. Lower average is the implicit assumption there. A random sample of the octane ratings is taken given these 20 numbers here. To save time, there's x bar, the sample observed value of the sample mean. There's the observed value of the sample standard deviation, S. I'm not pretending I know sigma in this case. And the sample size is 20. Let mu be the true mean octane rating for pumps at this gas station. For all the pumps, we're only doing a sample. Maybe this is a humongous gas station, or maybe they're sampling at different times. So maybe thinking of this as one gas station is a little bit fishy, but we'll go with it anyway. Write down appropriate null and alternative hypotheses based on the government agency's suspicion. Yeah, maybe it's better to imagine it's not just one gas station, but it's a bunch of gas stations for the same company. So this is really a random sample from those, but that's not the way it's stated here. Part A, write down, appropriate null and alternative hypothesis, H0, and alternative, our book calls it H1, other books call it HA for the alternative, on mu. Based on the government's suspicion. It's best to write down the alternative hypothesis first. They suspect, where does it say? Suspect. They have a suspicion, a theory, that it's too low. So the alternative hypothesis would be that mu, the true mean octane rating at this gas station or these gas stations, is less than 87.3. That's their theory. Which means the null technically would be mu is greater than or equal to 87.3, the opposite of this. We usually don't write greater than or equal to in the null. We usually just write equal to. That's good enough, you might say, because if we can reject the null hypothesis at this boundary value of the null 87.3, then we can reject it at other values for the null bigger than 87.3. Okay? So we usually just write an equal sign there, make it a simple hypothesis. There it is. Part B, should the null hypothesis be rejected at the 0.05 level, make a decision based on computing an approximate p-value, either with a calculator or a table, show your work or explain. Okay? So what do? Well, what is a p-value? P-value, and you can ask many scientists on the street what a p-value is, even though they use it all the time, they will often get it wrong. It is what? It's the probability of observing a test statistic as extreme or more extreme as what you actually observed under the assumption that the null hypothesis is true. Okay, that's a mouthful. There's two different ways of thinking about the test statistic. You could think of it as being an x bar, this x bar here. You could also think of it as being what's called a t statistic, like we did in the very first problem. Since we don't know the population standard deviation here, there's a t statistic that's appropriate. Let's write it initially in terms of x bar. X bar is 86.865. That is smaller than 87.3, and the alternative hypothesis is less than. So as extreme or more extreme in this situation is a less than or equal to, because it's a left-tailed test. Left-tailed test. Because it's a less than sign. If it's greater than sign, it's called a right-tailed test. If it's a not equals to, it's called a two-tailed test. What do we actually observe? I should make a capital X bar here, actually, because I'm thinking theoretically. There's our actual observed X bar. To think about the p-value, I should really think about the random variable capital X bar. What we actually observed was 86.865. Technically speaking, this is a conditional probability. Based on the assumption that the null hypothesis is true, assume mu is 87.3. As far as calculating this goes, we want to convert to z, especially if we want to use a table. And I think it's good even if you use a calculator to do this next calculation. Emphasize what you're doing here. We are going to standardize this using the assumption that the true population mean is 87.3. So we're trying to figure out what are the chances of observing this. We need to subtract the true population mean and divide by the true population of the standard deviation, which we really, oh, that reminds me, okay, I made a mistake here. This should be a t because I'm using the standard deviation s from the sample. It's based on also 19 degrees of freedom. Gamma, or df, is 20 minus 1 is 19, so t19. What we divide by is s divided by square root of n instead of sigma divided by square root of n. So this is 1.07668 divided by square root of 20. I could also just call this an observed t statistic. I could just label it t. Don't put a subscript there because we're not talking about an area to the right. This is just an observed value of a t statistic. That's another way to approach this. And what will it equal? Okay, 86.865 minus 87.3. The numerator is negative 0.435. The denominator is going to be a pretty small number. Let's just do this. Divide by, in parentheses, 1.07668 divided by square root of 20. End my parentheses here, like that. Yeah, the t statistic here is about negative 1.807. It's approximation that t19 is less than or equal to negative 1.807. Let me do the table as well as the calculator. Using a table does get a bit confusing here. Think about it in terms of an area. This is going to be some area under, well, a t distribution with 19 degrees of freedom that will be centered at 0 to the left of negative 1.807. We're trying to find that area right there. The tables typically give you areas to the right of positive numbers. What you need to do is you need to use the symmetry of the distribution. The area to the left of negative 1.8087 would be the same as the area to the right of positive 1.807. And if you look in the t-table, based on 19 degrees of freedom, so we all have positive numbers there. 1.807 is between these two numbers. That means the cumulative probability is between these two numbers, which means areas to the right are between 1 minus these two numbers, which would be between 0.025 and 0.05. The p-value is going to be between 0.025 and 0.05. Relatively small p-values, small enough to reject the null hypothesis at the 0.05 level. Okay, that was kind of tricky. And so yeah, we are going to reject the null. Let's use the calculator to do this as well, to confirm this. The nice thing with the calculator is you could just use the statistics, and I do have in the stat menu in list 2 the numbers for this problem, 86.1, 85.9, etc. And when you go to back to the main stat menu and go over to tests and do t-test, you can use either data or stats, data meaning the actual data from list 2, or the stats that you see here, x bar, s, and n. And I can just use the data. The null value is 87.3, it's list 2, frequency is 1, it's a left-tailed test. Calculate this. Oops, that's wrong. Stat. Okay, there we go. We get the same t-stat, negative 1.807, p-value about 0.04, okay, which is between 0.025 and 0.05. P is close to 0.04. Oops, I lost it here. Yeah, close to 0.04. There's x bar, there's s, there's n. Degrees of freedom is not written here, but it's 19. 0.04, less than alpha, reject the null. Okay? So what does that mean on a practical level? We're rejecting the null. It means we think that their pumps are faulty, their octane rating is too low. We think the alternative is correct, and we're going to find them. Okay? But it could be wrong based on just the luck of the draw with the sample. They could be in compliance. That's possible. To what type of error are you now susceptible to? Type 1 or type 2? When you reject the null, which is what we're doing here, we're susceptible to a type 1 error, which is like, in a courtroom, convicting an innocent person. Right? It's an error. You convicted a person who's actually innocent. The null hypothesis is innocence, essentially, or the assumption of innocence. The alternative is guilty, or the conviction. When you reject the null, say they're guilty, but they really are innocent, that's pretty bad. That's an error. It's called a type 1 error. And we have rejected the null here, so we are susceptible to that. Susceptible to. How do you spell susceptible to? Susceptible. It's an E there. To a type 1 error. Reject the null when it's true. If the decision had been failed to reject the null, or accept the alternative, or no, accept the null, then we're susceptible to a type 2 error. That's like in a courtroom where you failed to convict a guilty person. I don't know what I'm saying here, but couldn't figure it out in part B. Say what to do here if you could have figured it out. Okay, I'm just saying if you made a mistake, if you couldn't figure out what to do for part B. Say, if I reject the null, I'm susceptible to a type 1 error. And if I don't, then I'm susceptible to a type 2 error in case somebody couldn't figure out part B. Part D, what are the practical consequences of such an error? You'd be fining an innocent gas station. Fining an innocent gas station. Innocent gas station. Okay? And that would be bad. But a type 2 error is also bad. You'd be failing to fine a guilty gas station if you made a type 2 error and you failed to reject. All right, to the next problem. One of these long problems, but take it step by step. It's thought that a majority of procedures used in a statistical computer package run in less than 0.1 seconds. To verify this contention, a random sample of 20 programs is tested, examined. Let P be the true population proportion of procedures that run in less than 0.1 seconds. We are therefore testing this. Why this? It's a right-tailed test because of the word majority. It is thought. The theory is that most procedures run it in less than 0.1 seconds. We got to test that. So it's a hypothesis testing situation. Directions. A, let X denote the number of programs where the procedure is used runs in less than 0.1 seconds from a sample of size 20. Number of successes, you might say, in 20 trials. This is looking like binomial. Yes, binomial random variable. It can be shown that the probability that X is greater than or equal to 14, assuming the null is true, is about 0.05. It's actually a little bit bigger than 0.05, but pretend you don't know that and just go with it being about 0.5. What then is the critical region for a 0.05 test? What does this mean? A critical region, call it C, is a set of values that lead to rejection of the null hypothesis. In the previous problem, the critical region, also sometimes called the rejection region, in terms of X bar, we rejected here, would be some range of values less than or equal to some number close to 86.9 perhaps, or 86.87 or 88. All numbers less than such a number would lead to a p-value less than 0.05, and you'd reject the null. That's what we mean by critical region. This is a discrete case, though. X can only be a whole number. Since this is 0.05, the probability that X is greater than or equal to 15, as another example, would be less than 0.05. And greater than or equal to 16 would be even smaller, etc. Those are probabilities that are less than alpha, or less than or equal to alpha, if assuming we're so close to 0.05 that it's effectively 0.05, even though it's actually closer to 0.06, but pretend you don't know that. Based on that approximation, just to keep things simple, what's the critical region? What values of X will lead to rejecting the null? 14 or higher. 14, 15, 16, 17, 18, 19, and 20. That's the answer to part A. Part B. When the test is conducted, 13 are found to be run in less than 0.1 seconds. Will the null be rejected? Why? To what type of error are you now subject? This observed value of X, 13, is not in the critical region. The probability that X is greater than or equal to 13 when the null is true is a fair amount bigger than 0.05. We're going to fail to reject. Fail to reject the null. Some people say accept the null. It's usually better, I think, to say fail to reject, because it's not that the null's true for sure, it's just that you don't have enough evidence to reject it. It's like you're the prosecuting attorney. It's not that the defendant is innocent, you just didn't have enough evidence to convict them in your mind as a prosecutor. Fail to reject the null because 13 is not an element of the critical region. 13, this is not an element of, or you can just write out the words too. 13 is not in the critical region. And since we fail to reject the null, we're subject to a type 2 error. Subject to, I guess that's simpler to write than susceptible to. A type 2 error because we failed to reject the null when maybe we should have, because maybe it's false. Oops. One period. Part C. Find beta, the probability of a type 2 error. Type 2 error is when you fail to reject the null when you should have, because it's false. The alternative is true. P is bigger than 0.5. But in order to calculate such a probability, we need to assume if the truth is really that P is 0.7. This is a theoretical calculation, really. You don't truly know what P is. So when you do calculations like this, you're making hypotheses. You're wondering, what if P is 0.7? What then is my probability of making a type 2 error? Beta. Failing to reject the null, X being less than or equal to 13, given that little p is truly 0.7. So I'd have to calculate a binomial probability based on that p, and n is 20. Use the technology. Go to your distributions menu, again above the variables button, second distributions. We're looking for binomial here. Binomial CDF. Number of trials is 20. Probability of success is 0.7 now in thinking about type 2 errors. And the x value is the boundary here, 13. Fairly high probability, I mean not super high, but relatively high for making an error, 0.392. You'd think if you want, in general, you'd want to keep the probability of an error low, like less than 0.1 maybe. So that's relatively high. This is maybe not such a good kind of test. And the power of the test, which is part D, if the truth is 0.7, is just the complement of this. The power, assuming p equals 0.7, is your probability of correctly rejecting the null when you should, because the alternative is true, assuming p is 0.7. Probability that you are in the rejection region, given that p is 0.7, 1 minus this probability, 1 minus beta. So you don't have to do much more work. You just do 1 minus 0.392, and that'll be 0.608. That's the power in this case. Not typically high enough. Typically, when you shoot for 80% power, you typically shoot actually for beta to be less than 0.2 in most statistical studies. And sure, I mean, if the power is bigger than 0.9, that's even better. So, yeah, what would we do to get a more powerful test here? Well, maybe the sample size of 20 is just too small. Maybe you should use a bigger sample size, and that might make it a more powerful test based on a new rejection region for a bigger sample size, based on still using alpha to be 0.05. That would be one way to increase the power and decrease the probability of a type 2 error. By the way, alpha is the probability of a type 1 error. You always decide when you choose alpha what you want to be the probability of a type 1 error. That's a fairly small value. That seems good. But the probability of type 2 error is too high. The power is too small. So you probably should increase the sample size. The next problem is also about power and alpha and beta, but it's a bit more theoretical. It's actually quicker to think about, but you still need to understand concepts. You need to know your facts as well, like the distribution of the sample mean x bar. Sample of size 10 from a normal distribution with variance 250 is used to test a null that mu equals 50 versus an alternative that mu is a null that mu is 40 versus an alternative that mu is 50. Don't let the atypical form of the alternative bother you. Usually it would be a less than or greater than or not equal to. But just to keep things simple, for the sake of doing the problem, we assume mu takes on a specific value. It's more like the power calculations and the beta calculation from the previous problem. The test stat is the sample mean, x bar, which makes sense. That's an unbiased estimator for mu. Let us agree to reject the null and favor the alternative if the observed value of x bar is greater than 47. Why not 45? Well, you are typically trying to make it harder on yourself to reject the null. You want good evidence before you reject the null. You want alpha to be small. So it's typically, in this kind of setup, more typical to make the rejection region closer to the alternative value if you're using a simple alternative like this, mu equals 50. So 47 or greater would lead to rejection. That's the critical region in this case. It's a continuum of values, and this is a continuous situation. Part A, if the null is true, what's the distribution of x bar? And also if H1, the alternative, is true, what's the distribution of x bar? Okay. You could think of this in terms of the central limit theorem, if you like. You actually don't have to, because you are assuming you're sampling from a normal distribution. But even if you weren't, the central limit theorem would still apply to say x bar at least is approximately normal. Here we can say, because we're sampling from a normal distribution, that x bar is in fact truly normal, with mean equal to the population mean. And if H0 is true, that mean is 40. When H0 is true, and variance equal to the population variance, sigma squared, 250, divided by the sample size 10. That would be the variance. So this is normal with mean 40 and variance 25, which means the standard deviation is 5. That's your sigma squared here. Oh, I shouldn't use the populations. It's the sigma squared for x bar, not the population itself. If you use standard deviations there, you would want to write a 5. On the other hand, if H1 is true, what is the distribution of x bar? Still normal, still the same mean, different mean. Still going to have the same variance. The mean now is 50 because now I'm assuming H1 is true. Now I use a 50. The variance is still 25. Okay. Part B. On the same set of axes, draw graphs of the distributions, the PDFs of x bar, normal curves, from part A. Next, clearly shade graphs of the distributions. Shade and clearly mark the regions whose areas represent alpha, beta, and the power. Okay, so draw a number line. One of these distributions is centered on 40. One is centered on 50. They're both normal. Let's try to draw a reasonably accurate graph. So the variance of these x bars in both cases is 25, so the standard deviation is 5. So 45, while it's not the boundary of the critical region, is the location of the inflection points on the graphs of these normal curves, because that distance there is 5 and this distance is 5. So that'll help me draw it a little bit more accurately. So I want normal curves whose inflection points are at 45. And also for this one on this side, it would be at 35. Doesn't have to be a perfect drawing. So there's if h0 is true, where mu is 40, centered on 40. And another picture if h1 is true, centered on 50, still with an inflection point of 45. For my students, if this was on the test, again, your drawing doesn't have to be perfect. So I'm just trying to get the right idea. You don't have to get these inflection points exactly right. I'm just trying to do it here. Over there, this is if h1 is true. Mu is really 50. This is centered on 50. These would be the sampling distributions of x bar. Alpha is the probability of a type 1 error. Probability of rejecting null when you should not have, because it's true. The rejection region is 47 or greater. 47 or greater. When x bar is 47 or greater, we reject the null. That's the rejection or critical region. Everything greater than or equal to 47, say. And everything less than 47, you fail to reject. So the probability of a type 1 error, alpha, is when you reject the null when you should not have. You're in the critical region when the null is true, when the red graph is the true distribution of x bar. So the probability of making such an error is the area under this red graph to the right of 47. That's alpha. Beta is the probability of a type 2 error, failing to reject the null when the alternative is true, so you should have rejected the null. h1 is true. The green graph is the true distribution of x bar. What are the chances of failing to reject the area under the green graph to the left of 47 when h1 is true? That is beta. The power is 1 minus beta. It's the area under the green graph to the right of 47. That is the power, and that's fairly large. So in this setup, it looks like alpha's smaller than beta, smaller than the power. And the power is 1 minus beta. Not taking the time to go ahead and compute those numbers, just thinking about it conceptually. Part C says, for a fixed sample size n, which we got here, 10, explain why decreasing alpha will increase beta. What's the corresponding effect on the power when alpha is also decreased? What does this all mean? What does it mean to decrease alpha? How can you possibly decrease alpha? That might be mysterious. Well, it's a matter of choice. You're going to choose to decrease alpha. How? By changing the rejection region, changing the boundary value, the critical value leading to rejection. Make it bigger. That'll make the purple region smaller, right? The red and green graphs stay where they are. The null and alternative hypotheses stay the same. I can change where I choose to reject. I could make it 48 or 49 or 48.3 or something like that. To decrease alpha, the red and green graph stays the same. If you make the purple region smaller by increasing the 47, make it larger, that's going to increase beta. And that would be your explanation. Explain why, okay? the rejection, the critical value moves to the right, making alpha smaller and beta larger. It increases the area shaded this way as this number moves to the right. What's the corresponding effect on the power? Power is 1 minus beta. It's going to decrease the power. Since power equals 1 minus beta, it decreases the power. And so what this means, as far as this last question goes, practically speaking, is for a fixed sample size, you can't have it both ways. If you want small alpha, it makes beta larger. If you want small beta, it makes alpha larger. Said another way, if you want small alpha, it makes the power smaller, which is bad. If you want larger power, it makes alpha bigger for a fixed sample size. I'm not going to write that. That's what I verbally said to save time here. I won't bother writing that. Can you have it both ways in some other way? Yeah, you can increase the sample size. But there's cost there too, like monetary costs. When sample sizes are larger, it costs more money. And it also might take more time. So time and money are what you lose out when you make your sample size too large. But for fixed sample size, you can't have it both ways. All right, we are on getting close to the end here. I have 2 more pages, but these I think will go quicker. Yeah, I can go quicker on these here. Assume you keep track of your golfing scores for your entire adult life, and they happen to have normal distributions. Okay, to keep things simple, so these theories apply. In real life, might not have a normal distribution, but it seems reasonable. A random sample of 5 of your golfing scores yields these data. Find a 90% confidence interval for your true mean score mu over your whole adult life. Report your mean accurate to 1 place after the decimal and your margin of error to 2 places after the decimal, just for fun, I guess. Usually you'd want the same number of significant digits or same places after the decimal. Hey, confidence interval. We did that near the beginning to estimate a mean. But at the beginning we had sigma. It was the Hobbit problem. We knew sigma. Here I'm not telling you what sigma is. This is more realistic. The formula starts out the same, and in terms of a random variable, still start off with an x bar, plus or minus, but now you use a t distribution. And there's a certain number of degrees of freedom you have to think about. Instead of z sub alpha over 2, it's t sub alpha over 2. And instead of sigma over square root of n, it's s over square root of n. And the degrees of freedom, df, or gamma if you prefer, is n minus 1 in this setting. N is 5, so this is 5 minus 1, or 4. By the way, degrees of freedom is not always n minus 1. Don't make that mistake. For example, when you do simple linear regression, degrees of freedom ends up being n minus 2. And when you're comparing means, things can get very nasty as far as the degrees of freedom. This is just the simplest kind of situation. So now we observe values for these things. My stat menu. I do have these numbers in list 3, 78, 91, 86, 101, 88. Yep, okay. Stat, calculate one variable stats. List, there's list 3. List 3. We get an observed value of x bar to be 88.8. We get an observed value of s to be about 8.34865. I'll use more places of accuracy that I might need just to play it safe. 8.34865. N is 5. What is t and what is alpha? It's a 90% confidence interval. 100 times 1 minus alpha would be 90. So alpha, 1 minus alpha is 0.1 and alpha is, 1 minus alpha is 0.9 and alpha is 0.1. So alpha over 2 is 0.05. So we're after t sub 0.05 based on 4 degrees of freedom. Let's just do that with Tn here. Distribution inv t. Again, 90% confidence interval. Alpha is 0.1. Alpha over 2 is 0.05. So the area to the right of the t value is 0.05. So the area to the left is 0.95. 4 degrees of freedom. This is about 2.13185. 2.13185. I think in the back of the book it just rounds it to 2.132. It's probably good enough to get the places of accuracy that we want. 2.13185 goes there. Let's just do this multiplication all at once here, times 8.34865 divided by square root of 5. Yes, sample size is 5. Degrees of freedom is 4. So this gives 7.9595. Rounding to 2 places after the decimal, that would be 7.96. So 88.8 plus or minus 7.96. We could also write it in endpoint form. I won't bother. We're 90% confident that our true mean golfing score on, say, a par, what would it be, par 72 or something, course over time is in this interval somewhere between approximately 81 and 97 or so. Okay, if we wanted more confidence, it would be a bigger interval. The margin of error would be bigger. Number 11. One source of water pollution and gasoline leakage from storage tanks. One source of water pollution is gasoline leakage from storage tanks. Random sample of 100 gasoline stations is selected. We're picking on gas stations in this exam here, I guess. Then the tanks are inspected. 20 are found to have at least one leaking tank. Find a 95% confidence interval for the proportion of stations with a leakage problem. Proportion rather than mean. Though it is possible to think of proportions as means, but it's simpler not to. The formula for the confidence interval is p hat, sample proportion, plus or minus z sub alpha over 2. We go back to using z, times, not a simple fraction like this, but something more complicated, square root of p hat times 1 minus p hat divided by the sample size. Turns out to be what you put there. Where p hat is the sample proportion based on your random sample of gas stations, in this case, found to have a leak, sometimes written as x over n. 20 over 100 here, that's 0.2. That's your point estimate for p, the true population proportion. We want an interval estimate. 95% confidence, alpha is going to be 0.05, alpha over 2 is going to be 0.025, and this number is going to be your favorite 1.96. So this is going to be 0.2 plus or minus 1.96 times square root of 0.2 times 0.8 divided by 100. By the way, there's sometimes people do something called a Wilson estimate here for the confidence interval that in theory is sometimes better, but we keep things simple. So there's 0.2 times 0.8 divided by 100. Take the square root of that. Get 0.04. This whole thing is 0.04. Multiply by 1.96. Get a margin of error of about 0.0784. 0.2 plus or minus 0.0784 in plus or minus notation. Probably too many significant digits, but don't worry about it. As an interval notation, whether you use parentheses or square brackets, doesn't matter really. 0.2 minus 0.0784 would be what? 0.1216. And then plus it would be 0.2784. So there's your confidence interval. Part B says, assume there's approximately 400,000 stations in the U.S., find a 95% confidence interval for the stations with the leakage problems. Just need to multiply these numbers times 400,000. So 0.1216 is your left endpoint for the proportions with the leakage problem, times 400,000 gives 48,640, probably too many significant digits. Probably best to round it to 49,000 or something, but we won't worry about it. 0.2784 times 400,000 is 111,360. So we're 90% confident that the number of stations in the US with a leakage problem is between these two numbers, and it's probably best even to round to 50,000 to 110,000 might be the best thing to round to. How large a sample is required to estimate the proportion of stations with a leakage problem to within 0.01 with 95% confidence, assuming no prior estimate is available? It's a formula. The formula in my class's textbook looks like this. And the sample size is z sub alpha over 2 squared divided by 4d squared, where d is the margin of error. Some books use an m there. Some books also just take this thing as an initial fraction like this and square it. That's the formula to use for the sample size. And then you round up to play it safe at the end. When no prior estimate is available. When there is a prior estimate available, you can use a more complicated formula that gives you a smaller answer, but this is sort of safer to use. And so the margin of error here, d, is 0.01 that we want. The alpha is 0.05 again, so alpha over 2 is again 0.025. Z sub 0.025 is our old friend, 1.96. So we're going to get 1.96 squared divided by 4 times 0.01 squared. Or I could just do 1.96 divided by 0.01 first and then square that. And then divide by 4. Does turn out to be a whole number in this case, 9604. If it was not a whole number, if it was 9604.1, round up to 9605, even though it's not a real big deal. But, about 9600 is what it is. To get full credit, though, I'm saying round up to the next highest whole number. Last page. Long video. Let x1 and x2 denote the number of objects with a trait of interest independently drawn from samples of size n1 and n2. Random samples here. Assume these random variables are binomially distributed with parameters p1 and p2 and corresponding n1 and n2 as well. Part A, find the expected value of the pooled estimator p hat. By the way, this is going to be relevant in the last problem where we're going to be comparing two population proportions. We're going to need to pool two sample proportions. Expected value. So you could do this problem without really understanding what it's about, because you can just use properties of expected values. You can just, first of all, plug in this thing here, and then if you want to use properties of expected value, and you also want to use the assumptions, you're going to need to separate this into pieces like n1 over n1 plus n2 times p1 hat plus n2 over n1 plus n2 times p2 hat. And now use the linearity of the expected value operator. That's what you always have to use when you're trying to do something like this. We can factor out the constants. n1 over n1 plus n2 times the expected value of p1 hat plus n2 over n1 plus n2 times the expected value of p2 hat. That is one way to write the answer. Now, I probably should have added directions here to say you may assume P1 hat is an unbiased estimator for P1, and P2 hat is an unbiased estimator for P2, because I kind of used that kind of idea here in part B. I should have written that there. This is going to be P1, and this is going to be P2. They're unbiased estimators for those population parameters. P1 hat is an unbiased estimator for P1. That means its expected value is P1. Same kind of thing for P2. So you replace those with P1 and P2, and then you can combine everything back together, if you like, into one fraction to get N1 P1 plus N2 P2 over N1 plus N2. Okay? So kind of a funny steps to get to the answer you would think it would be anyway. But it's good to see that it works out. Part B, show that if the null that P1 equals P2 is true, if you're testing the equality of two proportions, either against an alternative that is either left-tailed, right-tailed, or two-tailed, show that if that's true, then P hat is an unbiased estimator for the common population proportion, P, which would then be, if these are equal to them. Note, individual sample proportions are unbiased estimators. I should have said that in part A as well. For the corresponding individual population proportions, you may use this knowledge. Show it's unbiased. Show the expected value of P hat is P. Well, by part A, it's this. But by this assumption that P1 equals P2 in the null hypothesis, which we're assuming is true, we can replace both P1 and P2 by P. And then you can simplify because you can factor out the P. You can write this as N1 plus N2 over N1 plus N2 all times P, which is just 1 times P, which is P. Done. Okay? And that shows that P hat here is an unbiased estimator for P, the common population proportion when we assume the null hypothesis is true. You might wonder, if you have two different populations, is it really going to be true that the null hypothesis of an equality is actually ever going to be true? Which you'd have to assume if it's a two-tailed test. And well, we always in statistics, when we're applying these probability ideas, we just assume things, even though it might not be technically correct. We just hope it's approximately correct. Last problem. One measure of quality and customer satisfaction is repeat business. A supplier of paper for computer printouts sampled 75 customer accounts last year and found 40 had placed more than one order. Similar survey conducted at the end of the current year found that 34 out of 50 ordered again, placed more than one order. Do these data support the contention that there's been an increase in the proportion of repeat business over a 2-year period? Explain based on the p-value for your test. This has got to be a hypothesis test. Comparing two proportions. And the null, as usual, is going to be a simple one that P1 equals P2. You can do other nulls in comparing proportions. You could say P1 equals P2 plus 0.1 or something. That's hardly ever done. People are almost always thinking about whether proportions are equal or not. And in this case, whether they're equal or there's been an increase. And pretend P1 is the current 2-year period and P2 is the one from a year ago. P1 current year proportion. I could do it the other way around. Maybe that would make more sense. Portion of customers with more than one order. And P2 is going to be the last year proportion of customers with more than one order as population proportions, parameters. And we think there's been an increase. We think P1 is bigger than P2. This year's proportion is bigger than last year's. There's been an increase. If I did it the other way around, then it would be P1 is less than P2. All right, let's just jump to the test statistic. With proportions, it's Z, not T. We take the difference of the sample proportions. It's really equivalent to thinking about these hypotheses in terms of differences, the null being that P1 minus P2 equals 0, and the alternative being that P1 minus P2 is greater than 0. So you look at the difference in these sample proportions, P1 hat and minus P2 hat. You might say minus 0 minus the null value, but since subtracting 0 doesn't affect anything, you don't have to put it. Divided by a square root that when you use the pooled proportion, this thing, pooled estimator, can be written in terms of that as p hat times 1 minus p hat times, in parentheses, 1 over n1 plus 1 over n2. Where does this formula come from? It comes from some theory that we're not having the time to go into here, but that's what it is. So we got to find these things. P1 hat is, that was the current year, so that's 34 out of 50, and that's going to be 0.68. P2 hat is last year, that's 40 out of 75, which is 8 out of 15, and that's not such a nice decimal. 8 divided by 15. Oh, I guess it's not too bad. Okay, 0.53 repeating. The pooled proportion, I can either use this formula for it. Let me go ahead and write that down. N1 P1 hat plus N2 P2 hat over N1 plus N2. So I could write 50 times 0.68 plus 75 times 0.53 repeating, all divided by 50 plus 75. Or I can actually just do x1 plus x2 divided by n1 plus n2. It's going to give the same answer. 50 plus 75, 34 plus 40 divided by 50 plus 75, which is 74 divided by 125. You get the same answer either way. Sorry, that was not on the screen there. Get the same answer either way. 74 divided by 125. It's 0.592. You could check it with this formula as well. 50 times 0.68 plus 75 times 0.533333, all divided by, 74 divided by 125 again. So that shows the same thing. That's your pooled proportion. Plug everything in. P1 hat minus P2 hat, 0.68 minus 0.5333. It's going to be 0.14 with a 6 repeating, divided by square root of 0.592 is p hat. 1 minus p hat is 0.408. And then 1 over n1 is 1 over 50, plus 1 over n2 is 1 over 75. Let's go ahead and figure out that square root first here before we divide. So again, 0.592 times 0.408 is that, times, in parentheses, 1 over 50 plus 1 over 75. Sorry, there's no way around some nasty calculations here. Take the square root of that, get 0.089728. 0.14666 divided by that is approximately 1.63 for this right-tailed test. So the p-value is the probability that a capital Z standard random variable is greater than or equal to 1.63 for this right-tailed test. As extreme or more extreme is what we actually observed. That'll be 1 minus the probability that Z is less than that, which I can do with the calculator. Normal CDF lowers essentially negative infinity, upper is 1.63. So 1 minus that is the p-value, about 0.052, which is near the boundary value people typically use of 0.05. And I don't say what alpha has to be, so technically speaking, you could be right either way in rejecting or failing to reject. You could say, well, I'm not going to write this, I'll just say it. You could say that's a pretty small p-value. Yeah, not less than 0.05, but small enough for me. I'm going to reject the null. I think that based on the sampling, that the proportion of repeat business has increased from last year to this year. Or you might be dogmatic about saying, hey, that's bigger than 0.05, so I'm going to fail to reject. It's not a real big deal in this situation. If you make a type 1 or type 2 error, people are not going to die. Type 1 error is when you reject the null when it's true, so you think it's increased when it has not, so you think you're doing better than you are. And then type 2 error is when you fail to reject the null when you should have, so you think it's the same when in fact it has increased. So it's not a real big deal. People are not going to die. You're not going to lose a ton of money probably, whether you make errors in this context. So it's kind of up to you. That is the end. Thanks for watching.